Okay, so we're gonna do the exercise that we ended the last video with. So notice that f of x is x times 3 over 4 minus 2x. So what we can do is simply find the power series expansion for this and then multiply it by x. So this is, well, let's just factor out the 3 as well. This is 3x times 1 over, and then there's, factor out the 4, we get 1 minus 2x over 4. This is 3x over 4 times 1 over 1 minus x over 2. And now we can use substitution. So this equals, by substitution, 3x over 4 times the series x over 2 to the nth power, and going from 0 to infinity, which is, the bottom is 2 squared, so we get series x to the n plus 1, because we have an extra x outside, and then multiplied by 3, divided by, and we have 2 to the n, but then there's 2 squared, so we get 2 to the n plus 2. And where does this converge? And this is true when we had replaced x with x over 2, so as long as x over 2 is less than 1, we're good, i.e. absolute value of x itself less than 2. So as long as x is less than absolute value, less than 2 in absolute value, this power series expansion holds true. Okay, so that was that exercise. We're gonna do the next portion, which is on differentiation and integration of power series. But before we do that, I probably should state a general result which allows us to do the differentiation. So let's call this theorem. So given a power series we'll say c sub n x minus a to the n, and starting at 0 to infinity. So this is a power series centered at a. A lot of the power series we've seen are centered at 0. And let's say this has a radius of convergence r. Then this series is differentiable on the open interval a minus r, a plus r. The actual interval of convergence may include some of the endpoints, but generally we speak of differentiability on open intervals, just by the nature of the definition of differentiability requires open intervals. And this series is differentiable here, where let's give this series, let's say this series is f of x, power series, f of x is equal to that series, where, so f prime of x, what is f prime of x? Well, it's the derivative of this. If you write this term by term, right, so note, because this starts at just c0, which is a constant, the derivative of a constant is 0, so you start off with c1, and then 2c2x minus a plus 3c3 x minus a squared, and so on. This is going to be the summation of c sub n times x minus a to the n minus 1, where n starts at 1 and goes to infinity. So you have c sub 1 plus, whoops, and then there's another n here, times n. Let me rewrite it in the usual order. Usually write it as n c sub n x minus a to the n minus 1. So this is our general derivative right here of this particular series, and where this series converges on a minus r, a plus r. So it has the same, so this is the same radius of convergence as the original one. Okay, and you can actually do it using the ratio test to check, but it's always going to have the same radius of convergence. It's possible that the interval of convergence changes. I'll mention that at the end here as a remark. The integral of f of x dx, notice that if f is differentiable, it's continuous, and so you can differentiate. This is going to be, well, I have a constant c plus c0 x plus c1 x minus a to the n, c1 x minus a to the second power divided by 2 plus c2, right? Originally we had c0 plus c1x minus a plus c2 x minus a squared, but that, when you integrate, becomes cubed divided by 3, and so on and so forth. So this is c plus summation. Well, I guess let's start the summation. The c plus c0x plus summation c sub n x minus a to the n plus 1 over n plus 1, where n goes from 1 to infinity. Okay. And also here, also for the differentiation, you have that, so note that the radius of convergence is also r, so that this series converges on a minus r, a plus r. So the only remark I'm going to make here is that, so remark, the interval of convergence may change after differentiation and integration. Okay, this is an important point that the book largely omits. Doesn't really talk about it, but we're going to talk about it because it is a bit important. And let's just dive into an example. This is kind of just symbolic in nature. Let's do the integration part, because that has the constant and it looks a little bit more funny than the differentiation part. So let's start with the integration part here. So integration. And what we're going to do is the following. We're going to do two steps. We're going to get a series expansion for 1 over 1 plus x squared using substitution. Here we're going to use this substitution to get this one. And then we're going to use integration to get a series expansion for tan inverse of x. Okay. And so let's go ahead and do that. That'll be our example for integration. So let's first find, so we know 1 over 1 minus x, same starting point here. 1 over 1 minus x is x to the n, and goes from 0 to infinity when absolute value of x is less than 1. Hence, we already saw 1 over 1 plus x is negative 1 to the n, x to the n, and goes from 0 to infinity, and this is also when absolute value of x is less than 1. From here, we can get to what we want, which is 1 over 1 plus x squared, by substituting x with x squared. So here we get negative 1 to the n, x squared to the n, when this is going to converge where x squared has to be less than 1 in absolute value. This is equal to negative 1 to the n, x to the 2n, and x squared being less than 1 in absolute value is the same as just the absolute value of x being less than 1. Okay? You can check that that's true. And so now we have a series expansion, and let's write out a few terms here, just so when we integrate, because we're going to integrate now in just a second. This is 1 minus x squared plus x to the 4th minus x to the 6th, and so on. So when we integrate, on the left-hand side, we get tan inverse of x. So this is kind of on the one side. On the other hand, when we integrate on the right, what do we get? We get x minus x cubed over 3 plus x to the 5th over 5 minus x to the 7th over 7, and so on. And how do we write that? Plus a constant here. Plus, so constant plus all of this. So what do we have here? We have tan inverse of x equaling a constant plus x minus x cubed over 3 plus x to the 5th over 5, and so on. And what we can actually do now is plug in x equals 0 to solve for the constant. So we're going to plug in, x equals 0. We get tan inverse of 0, which is 0 on one side, is equal to c plus 0 minus 0 cubed over 3 plus blah, blah, blah. So you get 0 for all of these terms, so c is also 0. So that implies c is 0. Hence, we have that tan inverse of x is exactly equal to x minus x cubed over 3 plus x to the 5th over 5, and so on, which in short, a little bit shorter notation, this is negative 1, let's say to the n plus 1, x to the 2n plus 1 divided by 2n plus 1, where n is going from 0 to infinity. I'm sorry, this is just negative 1 to the nth. Yeah, there we go. And we know this converges on the same interval. For the radius of convergence was 1, so here also we're going to have x less than 1, but it turns out it's a little bit more than that. Okay, so we know for sure because the radius of, so r was 1 for 1 over 1 plus x squared, hence r is 1 here as well. But the interval, it turns out you actually can plug in and check at the endpoints that things change a bit. So for example, if x equals 1, when you plug in an endpoint here, you get negative 1 to the n times 1 to the 2n plus 1 over 2n plus 1. This is negative 1 to the n over 2n plus 1. This is an alternating series that converges by the alternating series test. This converges by alternating series test. The 1 over 2n plus 1 goes to 0. The 1 over 2n plus 1s are positive. And the 1 over 2 times quantity n plus, it's a decreasing sequence. All the requirements are satisfied by the individual positive part terms, and hence this converges. And it turns out that if x equals minus 1, let me do that with a different color here, then what do we get? We get negative 1 to the n, negative 1 to the 2n plus 1. This is always negative, right? So what do we get here? We get divided by 2n plus 1. So this is the same as negative 1 to the n times negative 1, because negative 1 to an odd power, 2n plus 1 is always odd. If you have negative 1 to an odd power, that's always a negative 1. So this is negative 1 to the n plus 1 over 2n plus 1. This is also an alternating series. This is also alternating. And hence this also converges by alternating series test. So it turns out that this actually converges. This is true. So tan inverse of x is equal to negative 1 to the n x to the 2n plus 1 over 2n plus 1 for absolute value of x is less than or equal to 1, i.e. on the interval negative 1 to 1, closed interval. Okay. All right, so this was an example of integration for and finding interval of convergence. So let me leave you with a little exercise here. So we'll do differentiation in the next video. Exercise. So use the series for 1 over 1 plus x to find the series expansion for the ln of 1 plus x. And you're going to use integration here. Okay, we'll leave it at that for now. We'll do more in the next video.